Hi, this is Dr. Lesher, and this video is about kind of the history of how we figured out what an atom is and what it looks like. So let's start out back in the olden days. We're talking about the 1800s here, early 1800s, maybe even 1700s. When you burn something, it looks like mass disappears, and that's what people thought for a long time. So where did it go? And people started realizing that if you collected the gases that were generated during the burning of a match, for example, there's actually not a loss of mass, there's conservation of mass. Second question that came up kind of early on is that there was an awareness of the elements. They knew there was different elements that could combine, and the question was, can they combine in any proportion or just certain proportions? And the experiments showed that, for example, carbon, 3 grams of carbon, can combine with either 4 or 8 grams of oxygen, but not 1 gram, 5 grams, 7 grams. So this led to the theory of atoms, atomic theory, that there's a base unit of matter, and those units can really only combine in certain ratios. So the theory has 5 parts to it, that there's these tiny particles called atoms. Atoms of a given element have identical chemical properties, and they form compounds by combining in these ratios. And fourth part is that they can't ever be created or destroyed in a chemical reaction. So the law of conservation of mass can be understood by this model. We can rearrange these atoms, but we can't destroy them or create them. And then carbon and oxygen, because they have different atomic masses, those ratios that I showed before, the experimental results, that corresponds to atomic ratios of 1 to 1 or 1 to 2. And they can't combine in just any ratio. So next question, what is an atom? First, to understand the experiments that yielded information on what the structure of the atom is, we need to understand the 4 basic forces of nature. This is almost like a physics slide as opposed to chemistry. But the gravitational force is what holds the planets in orbit. And then there's 3 forces that are really relevant when we're talking about atoms and molecules. Electromagnetic forces, which can be kind of broken up into electric and magnetic forces, strong nuclear forces, and weak nuclear forces. So we're going to focus on the electromagnetic forces first. And this first picture shows kind of what's happening with electrical forces. Positive charges repel each other, negative charges repel each other, but positives and negatives attract. A magnetic force is slightly different, and a magnetic force applies to a charged particle moving through a magnetic field. And if you have kind of a horseshoe-shaped magnet like this and a charged particle going through, its trajectory is going to be deflected by that magnetic field. So, how did scientists discover atomic structure? A few experiments we're going to talk about in this video. And these were mostly happening in kind of the late 1800s, early 1900s. In the late 1800s, scientists were doing a lot of work with glass tubes containing gases and applying electrical fields to them. The cathode ray tube experiment was probably the most famous of these, and that happened in 1897. And then the oil drop experiment in 1909 and the gold foil experiment in 1913. So let's start with the gas discharge experiments, and these are not really attributed to any one scientist. There was a lot of scientists doing work with this. But if you have a gas inside a glass tube and you have some voltage plates within that glass tube, scientists noticed that the atoms of gases that were inside that glass tube would break apart if there was enough electrical field applied. And so you'd have negatively charged particles moving towards the positively charged plate and vice versa. And then J.J. Thomson's experiment was kind of a similar experiment, both a slightly different setup. Here we have the glass tube with the plates kind of all the way over here on the left. And then there's a second electrical field and then a third field, this one being magnetic. So what happened here is that the gases in the tube were being propelled, the gases in the tube were being, the atoms of gases in the tube were being split, similar to the previous slide, and the electrons, the negatively charged particles, were being accelerated through this positive plate here. And when there was only the secondary electrical field, so that's the field generated by these electrically charged plates here, the electron was deflected because it was attracted to that positive plate. But if there was a magnetic field at the same time that was kind of equal in magnitude, that could balance out that electron and make it go straight. And if there was only a magnetic field, that would have a similar deflection. So there's a lot of permutations to this experiment, but what was found was the ratio of charge to mass for an electron, and it's a negative value indicating the negative charge, and there's a lot of charge per unit of mass. Next is Millikan's oil drop experiment, and in this one, Millikan used an atomizer to put very small droplets of oil into a container. And again, we're seeing charged electrical plates. This was a really good way for studying the charges and masses of these particles. X-rays imparted negatively charged electrons onto those oil droplets. And then what was varied in the experiment was the charge of those plates. So let's see a little video. So the X-ray has imparted some electrons onto these oil droplets. And if we zoom in, we see the oil droplets falling between the two plates. Now, as we adjust the voltage on the two plates, we're slowing the fall of the oil droplets. And if we have enough negative charge down here to repel the electrons, they'll even start to move up instead of down. And this was done many, many times very carefully. And the fact that the fall of the oil droplets is governed just by mass and the gravitational pull, and then the rise, the upward force on the oil droplets is just imparted, or is just a function of the charge of the electron and the electrical field. Well, we know three of these variables. The only one we don't know is the charge of the electron, and so that was able to be calculated. So what's known at this point? We know that there's a positive charge in the atom and it's got a lot of mass. And then we know that there's a negative charge in the atom that has a much smaller mass. So those charges are equal but opposite, and this leads scientists to develop a model that's kind of proportional to the masses, that there's a whole lot of positively charged space and just a little bit of negatively charged space. This is sometimes called the plum pudding model or the chocolate chip cookie model, where the electrons are these small dots within the picture of the atom. So that was set out to be either supported or not supported, and the way that was done was Rutherford's gold foil experiment. And so this experiment has a thin piece of metal, gold foil, and then a source of radioactivity in the form of alpha particles, which are relatively dense particles that contain 2 neutrons and 2 protons. And then finally there's kind of a circular detector here. And as we shoot these little particles towards the gold foil, what was observed was that most of these particles kind of move right through the gold foil, but some of them are deflected. And let's see sort of how that would vary with the plum pudding model. So if I'm using this plum pudding model where that positive charge is really diffuse, it's kind of spread throughout the volume of the atom, nothing at all theoretically would happen to these alpha particles. The model that was created as a result of this experiment is that you've got atoms that contain a very dense nucleus. And so still, most of the alpha particles are passing right through that foil, but the ones that happen to hit or get very close to the nucleus are deflected or bounced back. So we learned that there is some area of very dense positive charge that it comes to be called the nucleus of the atom. So in the end, this is kind of our model that we're now working with. There's a large volume containing electrons and a very small volume containing a very dense nucleus. And an analogy I like to use here is that the size of the nucleus of an atom compared to the atom itself is like the size of a pea in a baseball stadium. And if you were to scale up the atom to the size of a baseball stadium, the pea, the nucleus, would have a mass of 250 million tons. That's how dense the nucleus is of the atom.